All right, so thanks a lot. And again, I apologize for the rant. I hope that it does not go on the record. So I'm Leonardo Linguaglossa, and I'm maître de conférence at TélécomParis. And today I'm going to talk about containerization and the magic of network containers. So before we start, I will briefly introduce the context here. And I have prepared some of kind of more practical activity at the end of the talk, so that we can appreciate a little bit what we are discussing here. So most of you are probably familiar with the virtual environments and virtual machines and containers and OpenStack and whatever, but I will try to give just the basics for those who are not familiar with that. So when we invented virtualization, we tried to package environments and to make the environments ready to use in no matter which kind of infrastructure that might be available. But the problem here is that even with careful design, environments may be very different, and actually an application developed for one operating system may work differently on other operating systems, even if they are of the same time, like Unix-like environments, like Ubuntu or Debian. So each application may require configuration libraries that may affect the pre-existing application. So what we see here, we see that if we virtualize an application, that may not be actually the good point, because we are also assuming that all set of libraries used by the application are all the same, are all up to date. But at some point they might become obsolete, they may change, and so there may be a sort of incoherence even within the same application. So the solution, that is what we use with containers, is to separate the application code from the libraries needed to execute it. And so we have a nice picture here. So what we try to do is to use a common engine that can separate application code, the dependencies, and a minimal operating system configuration, such that this application works exactly with the same dependencies and the minimal operating system configuration, independently on the version of those same libraries that can be installed on the operating system. So you may have found that there exist container images that work specifically with old code, and they are guaranteed to work with the same old code, even if you install it in nowadays equipment. So one of such examples are Docker containers. That is what we focus now. So Docker is basically a platform for packaging, running, and manage application, decoupling it from the infrastructure and providing isolation. So the architecture is shown here in this picture. We have an infrastructure that can be a PC, it can be a server, it can even be a virtual machine, it doesn't matter. Then you have an operating system on top of it, and the Docker engine, which will be used to package different applications or different versions of the same application. So the core of the Docker engine consists of three main components: a client that connects to the Docker engine via a command line interface, a host that is running the daemon, which accepts REST APIs, so basically that are the APIs used for communicating with the client, and it can store some Docker objects that are the containerized images. And finally, we have a registry that is basically a repository for containerized images. The standard repository is Docker Hub, it is remote, but you can run your own repository and you can run your own local registry. So the Docker workflow is very, very simple. You have a client, you issue some commands, you build, you pull, or you run containers. You communicate with the Docker host that is running the Docker daemon. And then you can generate images. You can pull images from a remote repository. and after you have the images, you can use the images in containers. So there are several clients that you can use. You can use the standard client for Docker. You can use the Docker Compose, that is an alternative client used to work with set of containers instead of a single one. But the principle is all the same. And if well, let me just show here. If you're familiar with Git-like kind of workflow, you have several states in which you can use the machines. So typically you have a Dockerfile that is a set of instructions on how to build a container. So when you do Docker build, you construct, you build, you create an image that is stored locally on your device. This image can be run and it can be stopped, it can be started again, it can be killed. And the nice thing is that once you have a container, there are two kinds of alternatives. In one situation, you are not using resources. So you're just using the resources necessary to store the container. And in another situation, you are actually using the resources. So like CPU, RAM, storage, network, etc. So the container is only using the resource when it is in the state of running. And in this case, you use the CPU, RAM, storage, network, and everything. But when the container is created or it is stopped or anyway, it is not running, you only use the storage needed to save the files, the configuration files. And so you can actually, for creating the image, you can even pull it from a remote repository. So this is not shown here. This is the situation where the container is created from a Docker file. But anyway, there are some kind of interesting thing about container. So the execution and isolation properties of containerized environments. So multiple applications can coexist in the same physical location. And the isolation is provided by the container technology. This isolation is very important for the networking part that we are going to explore shortly after. And thanks to the automatic management of the dependencies, you can run multiple versions of the same application. So there's some parameters may be mapped on the fly on containers. So I have introduced a little bit the context of containers and VM. So differently from a VM, you do not need a fully working operating system to run a container. Actually, the container image includes a subset of a minimal operating system. So we reduce the redundancy and we have a fast starting time. It is more flexible because the resources that are used are allocated on the fly exactly as a separate process. So there is no need to reserve a physical location of memory for running a container. It can scale dynamically with respect to the load of the application. So the drawback of this is that applications may affect each other as well as the main host, and we will see shortly after why. And you are bounded by the operating system that is running on the lowest level of your hierarchy. So we have seen before that we have our infrastructure. So the infrastructure, again, it may be a PC, it may be a server, it may be a virtual machine. But on top of this infrastructure, you are running a full operating system. On top of the operating system, you have the Docker engine. So, but this is true for all kind of engines for containers. And those containers images that can be executed, they must share the same operating system as the host, as the infrastructure at the lowest level of your hierarchy. This is actually kind of different from with virtual machines, where we can run, for instance, a Linux device on a Windows machine running VirtualBox, or vice versa. This is not possible with containers, and I will show you why in the next few slides. So there are a few commands here. I'm not sure it's interesting for every one of us. So you can check the version, list the available images, list the available containers, or run a certain container. You can detach and reattach again to the container when it is running. So from the registry, the operations that you can do are pulling images, pushing modification into the images, into the image repository. You can tag the image with some keywords that you may find useful for later searches. You can remove images from the local cache. So normally you don't need to specify a registry, because if no registry specified, then it automatically reverts to the main Docker Hub registry. So the source of the containerization in the Docker sense is the Dockerfile, which is basically a text file containing a list of instructions to package the application. You specify the operating system, the runtime needed for the operating system to run, the application and libraries, and some environment variables. So it's a very easy way to create a almost identical copy of an operating system that can be extended and can be modified further, and then it can be stored for dissemination and sharing. So an example of the Dockerfile is this one. So we fetch a node containing the Argon operating system. We provide some sample arguments. Then we can run some commands. So we can specify the working directories. So commands are all the commands that are shared, that can be used on your host operating system. So if you run a git clone, you need to be sure that your machine provides the git interfaces. If you run npm, you need to be sure that your machine is providing the npm interface. And then this is the magic that we are going to see later. You can expose some network ports that can be mapped to local physical ports in the host machine. Well, I talked about Docker Compose, that is an alternative image for the for Docker, where instead of using a single container, you create a set of containers linked into an application. And in Docker Compose, in fact, as you see in the right part, you can specify services and how to build those services. And then you can specify how to configure at the network level the services together at once. This is not interesting for the rest of the talk, but let's further look on what is this keyword that we always find cloud native. There is a nice quote that I can share with you after we stop recording the talk, because I don't want it to be on the record, but remind me if you're curious about that. So because everybody talks about cloud native, but what it is exactly, it indicates a paradigm shift in the way applications are actually developed. So from both the software architecture and the execution perspective. So what do you do in cloud native environments? You basically package functionalities in independent microservices, so that instead of having a monolithic approach where all the teams work together on maybe a core and then several layers on top of the same core, all functionalities must be distributed by default, and they must provide independent services, so that we call microservices. So why this is done? This is done to provide fault tolerance. So you try to isolate and you try to optimize each service independently, and you may have teams working on separate services in parallel, basically because they are independent of each other. This can provide horizontal and vertical scalability. We will see slightly after the differences in the two systems, and it take advantage of the cloud architecture that we have nowadays, with several cloud providers that can provide public resources as in public cloud, or that can install a private cloud directly on your premises. Of course, the challenges in this context is that it is difficult to shift towards a pure cloud native structure from a monolithic app. It is actually it is much easier to redevelop an application from scratch if you keep in mind that you want a cloud native approach. It requires organizational changes, for instance, in terms of how the team of developers work and how they refer to each other in their internal hierarchy. And there is a need, which is currently an open question, for standardized solutions for the problems such as security and privacy, because if we are able to manage those problems in strongly virtualized systems, so using virtual machines, this is still more difficult in containerized environments. Well, I talked about vertical scalability and horizontal scalability. The etymology is very, very simple. So you had a server here. Usually servers are organized in racks and they can be stored one on top of each other. So vertical scalability means that your application that is made of several components that are highly coupled, they are tightly coupled. If you need to scale this application, so you need to grow your service because you need more users, you need more resources, the only solution that you can do is adding RAM, adding CPUs, and basically this translates into buying new equipment and running more services, more servers one on top of each other. That is why we call vertical scalability. It means growing the resources for all the application at once. On the other hand, with the containerization, we can provide the horizontal scalability, because say that you have your application that is not tightly coupled, in the sense that you can physically distribute your services on different areas, in different bays, in different docking stations and whatever. So you can just distribute your component, and actually the scalability becomes horizontal, because you can distribute your component like in an horizontal fashion. You do not need to add resources on top of each other. You can provide load balancing. For instance, you can multiply this service in two, and having another set of resources assigned for the same service, let's say the ball service. And the ball service now is horizontally scaled, and you can provide a load balancing just to distribute your request, your workflow on multiple copies of the same service. So, and this is actually very specific to cloud native benefits. If your services cannot be distributed horizontally, you cannot provide horizontal scalability, and you need to stick with the vertical scalability. Alrighty, so that was just a brief overview of the containerization techniques. There are a lot of details that I cannot discuss right now, such as security or isolations, but I do not hesitate to ask me some questions at the end, because I have a journal, and I can provide some examples on how to do that. But okay, let's go with the basics of containerization. So now it's time to have some paintings. I again apologize for the visual effect. So in practice, a container is nothing more than a process. It is a process that is being executed on your device. So let me just do that. And Let me just do that. So when you have a process, what you have is typically there is a physical machine. So the machine may have physical interfaces. Let's call those interface Ethernet interfaces, ATH maybe 1 or 0. Okay, so those are physical ports that are mapped into your operating system. So in fact, if this is the operating system, you have a virtual representation of that physical device that is, let's say, ATH0 or ATH1. So this is the operating system that includes what we call the Linux networking stack. This is true for Linux systems, but it's basically common for all kind of operating system. What is the Linux networking stack? The Linux networking stack is the set of functions, methods, and APIs to provide L1, let's say L5 functionalities. L1, L5 in the TCP/IP protocol stack. So basically, the Linux networking stack provide you with the methods to send the packets on the physical Ethernet, to manage Ethernet frames at level 2, so using MAC addresses, accessing the MAC addresses, swapping the MAC addresses. It provides you layer 3 functionalities such as the OSPF if you want to run the open shortest path first protocol. It provides the L4 and L5 functionalities to manage TCP connections and to create, I don't know, HTTP resources. So this is done by the Linux networking stack. The Linux networking stack is typically one for the same physical machine. But now we are installing this Docker engine. Again, I am using Docker as an example, but it can be any kind of containerized service. It can be LXC, it can be another one. So this Docker engine now gives me the idea of running different machines on the same device. So there is, let's say, the machine M1 and the machine M2. So those machines need to access the same Linux networking stack if they want to communicate. So if they need to go outside of the wire and maybe connect to the internet. So if this is the internet and you have a server, so let's say this is a server, you need this machine to go through the same physical port and then go out maybe through a first router and then traverse the internet and then reach a server. But the other machine may want to do the same thing. So for Docker environments, those machines may be totally identical, which means that they may have a virtual interface that has exactly the same name in the two machines, which creates a lot of problems. You have the same MAC addresses, you may have the same IP addresses potentially. So you need a way to isolate the network spaces from one process to the other. And again, you cannot do this physically as in a virtualized environment with VirtualBox, because in VirtualBox, you have virtual machines, and the virtual machines, they have a dedicated space for the RAM, they have a dedicated space for their network, they have, you can clone also those machines, but this is more complex, but in general, you can isolate pretty well those environments. So the problem is how to provide different namespace. So how to separate actually the namespace, how to separate namespaces. And well, guess what? The solution is Linux namespaces. So namespace is a framework that you can use in Linux to isolate the namespace from one device to the other. So there are different tools that we can see right now for the rest of the talk. So we are going to check namespaces. We are going to check the Ethernet pairs. Then we are going to look at Linux bridges and virtual switches, and finally tunnel interfaces. So in order to do so, I suggest to focus at few examples. So the first one is the simplest one. You have a single namespace in a single node. So here, if I go here and I go here, so the first example, let's have it divided in 4. So in the first example is a single namespace, single node. So in the single namespace, single node, you have a single machine that we identify here. You have your Linux networking stack. So this is the Linux networking stack that is physically connected and manages the physical interface. And what you do is that you create a namespace within the machine. Let's call it namespace 1 with a separate Linux networking stack. So the Linux networking stack inside the separate namespace is logically independent from the main networking stack of the node that you have on the bottom. You can evolve from this by providing 2 namespaces on a single node. So you do the same thing, but you have 2 different namespaces. Then you can provide 2 namespaces on separate nodes, sharing the same L2 network. And finally, 2 namespaces on separate nodes on different L2, L3 networks. But let's make it little by little. So first of all, what is a namespace? The namespace is a copy of the network stack with its own routes, firewall rules, network devices, etc. So by default, a process inherits its network namespace from the parent. And so at the initialization of your machine, all of the namespaces are, there is a single namespace that is inherited from the init process. So, yeah.
Here we don't have containers yet.
No, because this is a technique to separate namespaces. In the end, Docker is using that to create containers.
Yeah,
so
but here we are on a host, right?
Like here we are in a host, but let's say the first 90% of the steps to create a container is to have a separate namespace. So then the 10% is providing isolations with C groups and managing all those containers all together. But I would say that once you isolate network resources and you provide the isolation of the networking stack, you are done with a container, and I can show you why.
Yeah.
I can show you why. So this is not interesting actually, because when you have a single separate namespace on a single node, okay, you still do not have interfaces. So how do you make those nodes to communicate to each other? Well, you can do with the Ethernet pairs. So a vEthernet pairs is a construct on Linux that creates a virtual link, a pipe, basically, with 2 endpoints, one input and one output endpoints. So those are represented as virtual Ethernet devices, and basically sending any data on one side corresponds to an immediate reception on the other side. As a corollary, if one of the vEthernet is down, the whole link is down. So there cannot be one vEthernet mono, how to say, what is this, the dual of a pair? It's a mono node, a single node. You cannot have a single vEthernet. It's always in pair.
And you can have the 2 namespaces on different machines.
You can have the 2 namespaces on the different machines. You can have the 2 namespaces on different machines on different L3 networks. So you can have all kind of combinations that you want. And now I have some code that I can share also afterwards if you want. So let's have a look on the example of a single namespace in a single node. So now what I'm going to run is I'm going to run some commands to create one namespace, to create one pair of vEthernet from the namespace to the main host. So this is the host machine. And we are going to make those 2 hosts communicate to each other. So in order to do so, I need to remove this. I need to remove this, and I need to connect to my Linux system. So probably online, this is going to be much more visible, but I will try to zoom. So let me see if it works. Yep. Okay, maybe I can do that. Perfect. So let's have a look at some of the commands that I will share here. So now I run this script where I try to create a namespace, and basically it's as easy as having a sudo IP netns add with the name of the namespace. Then what I am adding is a vEthernet pairs. So I add a vEthernet 1 and a vEthernet 2, and I link those two together. And so I am creating a pipe between those two virtual Ethernet spaces. Then what I am doing is that I am adding the one of the two endpoints into the namespace. Because once you create the vEthernet devices, those are dangling, let's say, they are hanging on the operating system. So you need to assign at least one of them to the namespace that you want to create. So after that, you just do the same things you would do with normal interfaces. So you assign IP addresses, you assign you turn the Ethernet link up, and then you have your connection with the two endpoints. So let's run this thing here. So if I do single namespace here, so what I'm doing is that I'm creating the namespace. I'm adding one vEthernet on the namespace, and I am configuring the IP addresses and everything that I have said so far. So now, just out of curiosity, let's check with IP A all the links that I have available. So with the IP, with this command, I am currently on the host operating system. And so I have my loopback interface, I have my physical interface, I have another physical interface. I have actually two physical interfaces here, ENP0, S3, and S8. And then I have a virtual Ethernet. One end of the virtual Ethernet, because the other end of the virtual Ethernet is going to be somewhere else. If I want to show the namespace that I have available, I can do sudo IP netns, and actually here I have a single namespace. I'm trying to zoom in. So I have a single namespace. I can actually create another one. So in order to create another one, just to see what happens, I want to go here, and I want to create another namespace that I call red, sudo IP netns add red. So I am just adding another namespace. So here you can see that on the bottom of my screen, I have now two namespaces. I have red and single namespace. And now again, let me create another vEthernet pair. So, but with other names. So sudo IP link add vEthernet 4, type vEthernet, peer name vEthernet 5. So now I added two vEthernet interfaces. And if I do again an IP all, you can see that the vEthernet 4 and the vEthernet 5 are now assigned to the operating system. So they are here. But before, I created the vEthernet 1 and vEthernet 2. Why the vEthernet 2 is not visible here? Well, it is not visible because this vEthernet has been assigned to my single container. So what can I do now to attach to this container? Sorry, to this namespace. Namespace. Sorry for the thanks for the precision. Because if I do sudo IP netns exec my container that was single and then I do bash, I am currently inside the namespace. But not only I am currently inside the namespace, I am inside the namespace and I am executing the process bash. Guess what? Now this is a container. Now this is a container with a separate namespace that is executing a full bash command line interface. And in fact, if I do IPA, I see my localhost interface and I see my vEthernet too. So the containerization was as easy as creating a single namespace and then running a process within this namespace. Because now my bash process is included within this network namespace. I have a virtual Ethernet device that has this address here. I can actually ping my outside Ethernet internet device that was 172.16.0.2, no, .1 is me. I can actually check here with the vEthernet one. I can assign another vEthernet 172.16.0.2 up. Sure, it's not permitted. So the idea is that now I can ping. So now I am pinging my other pair of the vEthernet that is currently on my host operating system. From a logical point of view, the two processes of managing the ICMP request reply and managing all the packet in, packet out, and managing all the possible data that you can use with this networking stack, they are separate because those two networking stacks are identical copies and they act independently. So let me go back here. Let me go back here and let me go back here. So now we are in this configuration. I am running these two different vEthernet. This vEthernet is connected to this other vEthernet. I can ping this one and this one. And what happens? Well, if this virtual Ethernet was somehow connected to my physical networking item here, I can potentially take one container and go to the outside world. How can I do that? Well, we can introduce another construct that is a Linux bridge. So a Linux bridge is a virtual switch or a virtual router that can act as a switch or as a virtual router between all the virtual Ethernet interfaces and one or more physical Ethernet interfaces. And this is the objective of the other example of double namespace in a single node. So now I have some other code that I will show. What we are doing right now is exactly the same thing. We are creating two different namespaces, again, with two different devices, two different addresses, two different copies of the Linux networking stack. We are linking all of those with the Linux bridge. Here, I can use any kind of technology that I want. It's not necessarily bounded to the Linux bridge. I can have Open vSwitch, I can have VPP, I can have a software router. I can actually even have a physical switch, as we will see in the second part. But so now the idea is that this Linux bridge can connect those different namespaces, one with each other, and both of them with the physical world of the basic Linux networking stack. So now let's go to yes.
I have a question. Why do you need the bridge?
Well, you need the bridge because those networking stacks are isolated. So they are not aware of each other.
Okay.
They are isolated. So you may take one vEthernet and take the vEthernet, but it's like connecting two machines with a cable or connecting two machines via switch that then can be connected to the external world. So it's a matter of flexibility. So yeah, you need this one to put all of the items together. And this is the objective of my other code here. So now I am inside the machine. I can do that. I cannot delete the. So let me see the double namespace, NS1 and NS2. So, okay, now I am creating the namespace here. I am creating the vEthernet interfaces. This time I am creating two pairs of vEthernet. I am adding the two Ethernet on the separate namespaces. I am adding the IP addresses in the separate namespaces. And then I am creating a bridge. So creating a bridge is just this one. So I add a bridge item of type bridge, and I call it BR0. And then I assign one of those bridge items, one of those virtual Ethernet onto the bridge. So in the end, everything should be connected to the bridge. So, well, now I should, well, I forgot if I need to actually cut the other namespace, but let me see. Okay. So for the moment, everything works fine. There was this link file, this message file exists because I'm trying to set some routes, but apparently the routes were already available. So now let me check here on sudo IP netns. So we have NS1 and NS2. Let me check with the environment the IP1 and IP2. So it's 02 and 03. I have a bridge IP that is 01. So normally, if I do sudo IP netns exec ns1 bash, I am here. I have config, I have the correct address. Let me check on NS2. I have the correct address. So if I do ping 172.16.0.2, yeah. So now those two namespaces are connected via the Linux bridge. And I can even ping the Linux bridge if I do 172.16.0.1. So what is happening here?
Sorry, you're pinging from
I am doing this one. I am doing this. Let me. Yes, I am doing this. So ping from here through here.
Okay.
And the reply, echo reply is doing this thing. Echo reply is doing this thing here. So the echo request is going this way and the echo reply is going that way. Then I also pinged the Linux bridge. So here, that is the BR0. So here it's not identified because BR0 is basically another interface. Let's call it here BR0. And so I was doing a echo request from here to here and then vice versa. So for the echo reply. So now I have two separate namespaces that can work in conjunction with each other, and they can use the Linux bridge technologies to connect to themselves. They are still isolated in the sense that if there is something happening on this Linux networking stack, let's say that there is an attack and the TCP/IP pipeline is broken, well, this is only affecting this namespace. The namespace 2, sorry, this was 2. The namespace 2 and the Linux networking stack of the host, they are not affected. So this is why with containerization is quite similar, even if it's very different from virtualization, because you can replicate your services n number of time. So I have n services copy. So 3, 4, 5, etc. If one of those services is broken, well, doesn't matter. You have all of the other copies. As a plus, you do not need to reserve all those services with a fixed amount of RAM. So let's say I do not need to assign 1 GB of RAM to all of those namespaces because they can opportunistically eat as much RAM as they need. And so you have a potentially infinite number of copies that you can host on the same device. Yes.
When you say they are separated, since they run on a single CPU, I mean, there is still the multi-programming and the level of the CPU. And so in terms of speed, or I mean, if you want to execute them concurrently, I mean,
you can assign, of course, you have mechanisms to assign a container to a separate CPU. But the idea is this one. I will show you here. So the idea
up to, I mean, if you are a single machine, up to the number of CPUs of this machine.
No, because you can run more container on the same CPU. So because a container is not a virtual machine or a physical machine, it's just a process. So in your machine, you are currently executing thousands and thousands of processes that they are then scheduled by the scheduler, and then the scheduler assign a bit portion of CPU just for a time slot. They are executed, and then the CPU is released for another one, for another process. A container is a process, so it follows the same procedure of the Linux scheduler to be executed. So you can potentially have 1,000 of containers, and they are only using the CPU if the scheduler decides to use the CPU.
There is something I don't understand. I mean, assume you have a finite number of CPUs and you multiply the number of processes, right?
Yes, yes.
You said container by processes. So you have to do some scheduling of all these things. You have separated logically, if I get it correctly, the naming.
Yeah.
But in terms of processing, I mean, if there is only a certain power for the thing,
of course
you slow down.
Yeah, of course.
Proportionally to the inversely proportionally to the number, right?
So let me show a little bit better. Yeah, I agree with your. I agree.
So in terms of separation, it's a logical separation.
Yes.
But not they are still entangled by the fact that they are run on the same CPU or CPUs.
Yeah. But so let's consider a single CPU. So this is a CPU. This is a CPU, and this is the clock cycles. So those are clock cycles. So you have a certain amount of clock cycle. When the clock cycle is active, you can use one arithmetical logical unit instruction. So you are executing a arithmetical instruction. So you have a scheduler. So this is a Linux scheduler. And then you have a list of processes. So P1, P potentially infinite. Okay. So when the process is being scheduled, it is being assigned a certain amount of CPU cycles that then are dedicated to this process. And then the scheduler releases for another process. Okay, so then there are other CPUs, and then there are other CPUs. Okay, so in one common CPU, you have, let's say, 2 gigahertz of frequency. So you have potentially up to 2 billion instructions per second. Okay, so what happens is that all containers, they do not have at the same time the same pattern of utilization, especially if you have, I don't know, a website, so you have request, and the request may be, so this is a time, this is the request arrival. And so the request arrival may arrive at this point, then it may arrive at this point, and then for another container, the request may arrive at this point, it may arrive at this point, and then for another container, it may be here and then here. So if you dimension your list of containers very well, normally you should be able to, because you will not need to use the CPU 100% of your time. You will need to use the CPU only if there is a workload, only if there is a request. And the requests are in a website, for instance, the requests follow a daily pattern. So they are higher during the morning and then they decrease during the night. In another kind of queuing system, you may have a Poisson arrivals. So you may model these as much as you want. But the idea is that you have a budget of CPUs, and those are concurrently assigned to different those budget of CPUs are concurrently assigned to different containers, but the containers follow the same scheduling as your system. And in my system, if I go here and I do px minus aux, I have currently much more than my CPUs of processes are currently active. Those CPUs are just not using 100% of my CPU. Like this one is using 78%. I don't know what it is. It's Firefox. This one is using 33.5%. It's again Firefox, so it's basically eating one full CPU. But all those others are 0.2, 0.4, etc. And for the container, it's the same thing. You have different processes. You do not need to allocate a separate CPU to a separate container, because you can potentially have a container that is never used, that is only used on the opportunity.
So if what you call the traffic or whatever is sort of polished, regulated, then, then I mean you don't have the constraint of multi-programming.
Yeah, exactly.
But I mean, if you don't, if you take the example of Poisson, then there can be an arbitrarily small amount of time, the number of requests, which is 10 to the 18.
Yes.
Then multi-programming will hit you. So things are only independent or separated, as you said.
Yes.
Under some assumptions on traffic.
And in fact, this is why the performance of container networks are not as good as when you completely physically isolate the resources, because you do not have the guarantee. Of course, if you are in the explosion of all requests arriving at the same time and you have 1,000 containers, those thousands of containers, some of them will contain the CPU, some of them will be lost in the contention. Sure, definitely. Yeah, no, this is a good point. Yeah. And this is also one of the reasons why performance is on the execution may be better, but from the network perspective, you may incur on this kind of security issues. Sure. Well, all right. So this was the end of the practicals. So we have I wanted to finish just quickly with the virtual switches and software routers. So I am currently using the default Linux bridge that is the standard in kernel Linux. So you have others that can be used. You can also use a kernel bypass approach if you want. So like with high-speed software routers, you try to avoid all the Linux networking stack and implement your own stack in a fast way, as we can do with DPDK or with Munchen or with other alternatives. So of course, here the trade-off is between the performance of not using the kernel and the stability and the features of having in-kernel networking items. So when you talk about software bridges and virtual switches, etc., we are not necessarily talking about SDN, because SDN is the separation of control plane and data plane. In a container network, you can adopt SDN or not. We are not necessarily talking about the network function virtualization, because virtual switches can work in a function chain or not. So a software network is just the implementation of the networking stack in pure software, instead of using the physical device of a Ethernet card or a wireless card. So you can, of course, having SDN and NFV on these machines, but it's not a one-to-one correspondence. All right. Yes.
So I'm trying to understand what you say. But so when you've created these containers,
yes.
So and you have this virtual switch. So if I understand correctly, so internally you would have some TCP controlling the interaction.
Yes.
In all the containers.
Yes.
And really you have So really the idea is that you split the machine into lots of small machines.
Yes.
Which are running on the same thing with independent naming and things like that.
Yes.
But their interaction is through TCP.
Their interaction is through the protocol that you deploy on them. Yes.
Okay.
So if you use UDP, they send UDP. But if you have a TCP connection between the two, you have TCP connections. Yes.
Okay, but the thing I don't understand is that, so I mean, for the external world, this is a single IP address. So you have created this virtual thing inside. And so how do you reconcile the...
Well, you can use the network address translation. because it's actually the last thing, one of the last things that I wanted to talk about. So with network address translation, you can do what we call the IP address pooling. So there is only a single IP address that is publicly visible by the world. And then, so like in this case, you can have this this situation here where, so let me change with the black. So here you have a single public IP. So let's say 1.2.3.4, and then here you can add on top of this what we call a NAT device. So the NAT device is storing the temporary transitions between local private addresses that are not non-routable. So they are non-routable, and so they are not propagated to the internet.
And so it's not based on the switch.
Yes, it can be a switch equipped NAT. So in the sense that
in the Linux bridge, sorry.
yeah, in the Linux bridge, but you can even it's not mandatory. You can have just a one-to-one mapping. If you have multiple interfaces and multiple IP addresses, you can definitely do a one-to-one map. So Docker allows you to do so. So you have like a physical public IP address that correspond to one of the internal addresses of the container.
And so if you split, if you have, so if you need communication between a set of containers on the machine and a set of containers on another machine,
yes,
then you have to solve this
yes.
locality problem, right?
Yes. So basically what will happen in that case is that you have, let's say, we have two machines. Let's connect those two machines with a wire. So they are physically connected. They are in the same L2 and whatever. So this is 10.0.0.1 and this is 10.0.0.2. So those are two IP addresses. They can connect. They can talk to an item. Here, what you can have is a virtual network, or maybe a virtual network of networks. So you can have a mini internet inside your machine connected via software routers with separate IP addresses. Here I may run OSPF, here I may run RIP, and here I may have my addresses in the 192.168/16, and here I may have it in the 172.0.0.0/24. So I have two different private networks inside of my machine. All of those are containers. So basically this means that you have C1, let's say that you have three machines here and three machines here. You have C1, C2, and C3 that are running OSPF, and they are connected via a software router with M1, M2, and M3 that are running RIP. And these kind of links, they are made by a software router. So
which is inside the container.
It can be on a separate container, or it can be on the local host, because it depends on what you want. If you want to control of your host to all the machines, you may have a software router here on the physical machine, because in this case it's easier for you to manage everything. But you can also package this software router within another container. Yeah, nobody blocks you from doing that. If you want a further separation from namespaces, yes, you can do that. So then you can do this other router that is managing all of these, and then you can have this multiple hierarchy. Yes.
Excuse me, I have a question.
Yeah.
It's Maurice Gagné on the phone. Thank you for the very interesting speech. I'm just wondering, what you have described is very close to the physical layer. You mentioned the problem of CPU cycle distribution. And I was just wondering, do you think that such techniques that we have presented here could be used to design the next generation of chips? Now we are dealing with, from what I have heard, we are talking about processors integrating, let's say, 100 cores, processors, in fact, with network on chip. Do you think that this type of technology that you have just presented could be applied not to traditional networks, but to the design of the next generation of processors, network on chip?
Well, yes, I think so. So the fact is that when you go closer to the chip, when you go closer to the electronics, all of the developments that you can do at application layer becomes a little bit less practical, in the sense that when you were talking about the CPUs and the hundred of clock cycles, okay, so even inserting one application layer instruction may correspond to multiple clock cycles, because this instruction must be translated into more low-level instructions, and so it's quite difficult to put high-level logic into low-level.
Okay.
So, but I mean, definitely, it makes sense, because there are a lot of interconnections between those two. And in fact, one of my current works are exactly studying that. So the interconnections between how the application layer logic can be translated into physical CPU cycles. You know.
And I presume that concerning what you have said about the distribution of clock cycles by, I should say, ponderated weighted round robin between different process. What about RAM management when you have to deal with on the same chip to deal with multiple, I should say, operations? What is it an important aspect, or an aspect that is particularly investigated concerning the RAM management of, for instance?
Yes.
Yeah. Oh, okay. And can you say a few words about that?
Yeah, of course. I mean, the fact is that I for simplicity, I talked about this weighted round robin scheduler, but in practice, you have a plethora of scheduling techniques. So you have a deadline-based scheduling, you have fair scheduling, you have FIFO, you have a lot of scheduling algorithms that you can use. And of course, depending on the algorithm, performance may vary. Yes.
Yeah, but concerning RAM specifically, not CPU cycles, but concerning RAM. It's an aspect that is particularly investigated. I presume it's part also of the problem. I presume.
Yeah. So in container, in virtual machines, no, because you have a static allocation of RAM. For containers, RAM is treated as a commodity like CPUs. So in that case, yes, it's important. So in that case, the scheduling may also affect the RAM patterns. And again, this is one of the aspects that I am investigating in my current project.
Okay, thank you.
Yeah,
thank you very much, Leonardo.
Thanks, Maurice, for the questions. And well, I think we may just jump to conclusions because it's quite late. But so basically, what I showed you here is that we need isolations of resources, CPU, memory, and disk, and containers in particular need also abstraction for networking, which may span several nodes on the same machine, several nodes on several separate machines. So the keys to container are using abstractions provided by Linux, like namespaces and bit pairs, and adjusting the routing rules according to your needs. We didn't have time, but I have more slides if you're interested. And finally, virtual switching and software routing. Again, we ignored the details of security, isolation, C groups, malicious interactions, etc. But there's a huge lot of things to tell about that. So if you are curious, or if you want to explore more and want to collaborate, so please feel free to tell me. And this concludes my talk.
Thank you very much.
Thank you. Yeah, please go ahead. It's Maurice. Yes.
Yeah. Thank you.
Thank you.
I thought it was a question. So, if you have questions in the room. Yeah.
So, assume you have a lot of applications. I mean, high level and you have a set of machines. So there is probably the exercise for distributing the containers on the various machines in a clever way.
Yes.
So is this investigated?
Yes, yes. This is called the problem of the placement of the workflow. It's workflow placement, and it's true that is more in the context of virtual machines, because there you have it's easier to model because you have a static allocation of you have exact number of RAM CPUs dedicated to each workload. So in that case, you can model it much better. In this case, you have to add another layer of contention, that is the internal scheduling, and the fact that a container may scale from 0 to 100% of your CPU depending on the workload. So this is more complex to model, but it's a problem that exists, and it's called the placement.
Is this linked to what people call orchestration?
Yeah, exactly. So all of those things are connected. So orchestration is just basically how you have a set of services that you want to run all together, and so you need to place them not only to respect some network bandwidth or CPU usage, but also some constraint of the service latency and execution time, etc. So there are a lot of it's a kind of multi-resource optimization problems. So you have not only a single set of constraints, you may have several constraints in opposition to each other, and so it becomes very, very complex. There are a lot of heuristics-based work that I've seen. So not a lot of optimal closed-form solutions because it becomes impossible. So a lot of people are just doing heuristics and doing that.
Okay.
Other questions in the room? Or online? I think no. So thanks again, Leonardo.
Thank you very much. And thanks for you.